let's see, how many did we get there? There was 2, 3, 4. We can get 5. All right, so we'll do all those predictions. Nope. Okay, so that would be 2 waves there. So basically that's 1 wave and that's 1 wave. So L is equal to 4 halves lambda or 2 lambda. The wavelength is half the length. In other words, that's the wavelength right there. There's another wavelength.
What are you doing right now?
Pardon? This is the 4th harmonic.
Okay.
We're going to do 5 harmonics because we can get 5 harmonics off of this. And then the last one that we can get off that easily . So L is equal to 5 halves the wavelength, or the wavelength is equal to 2/5 L, or for the decimal fans, 0.4 L. So that's the nice perfect board demonstration of that. So let's see how close that gets to reality. Depends on how much imagination you have. All right, the first harmonic we're not actually going to hear, but let's go ahead and go through the process that we'll be using for the other 4. I know that the speed of a wave is 343 hertz. Right, that one again, 343 meters per second, based upon what Hope was saying. And that is equal to the frequency times the wavelength. Now the wavelength is going to be 2 times L. What is L? Well, that length there is L. Now I do have to stretch it out some. It is sort of bent on its own. It is plastic after all. It's cheap kid's toy. And I'm going to just stretch it slightly because as I spin it, it will stretch out just a little bit. And we have about 84 centimeters. So L, 0.84 meters. Therefore, what is the wavelength for the first harmonic? Say it again.
It's just half, right? So 0.42? 0.42? Oh.
Wrong way. Ooh. I know you got that, but you misread, I think.
1.68.
Yeah, 1.68. It should be twice that. The wavelength is twice L. All right, so first harmonic. The wavelength should be 1.68 meters. And so the frequency is 343 divided by 1.68. And we get 2 something.
204.166667.
Units?
Hertz?
All right. I assume all of you are highly trained musicians and can tell. There we go, first harmonic. We're nailing it, right?
A whole symphony.
All right. Let's see what it actually sounds like. Or at least get this going, and we'll do the prediction for the second one. Oh, it's already up. Yay. 202 point, I think it only goes to 1 decimal place there. Forgot, it doesn't like the keypad. All right, that's 202 hertz right there. But the first one we hear, not quite the same. So let's do the next one, and should sound closer to that. So the second harmonic, what is the wavelength?
0.84.
Yep. So the frequency would be 343 divided by 0.84, which is 4.08.
No, it's
So 408 point.
3 repeating.
And if you recall back, that's exactly the tone that we heard, right?
Yep.
Yeah, nailed it. All right, so how can you actually tell if two notes are the same? Now, there's a certain intuitive sense I think people have, but that's a speaker and this is a piece of plastic. The tones are, I think the official word is the timbre, is going to be slightly different between the two. Any people who've taken enough music to be able to correct me? And we're going to have to trust that I'm using the words correctly. So the timbre, or timbre, T-I-M-B-R-E, is going to be a little bit different because the instruments, the medium of the instruments are different. But there should be some way of being able to tell if that's the note we just heard. So I'm going to introduce you to beats. So what I did is I just made a graph of two oscillating waves. There we go. Blue and purple. So these are not identical. They look roughly at a quick glance the same. Notice that this one is sort of on the way down at the end, and this one has just bottomed out at the end. So they are slightly off of one another. I then took, I believe it was the blue one. I took the blue one and just traced it onto this clear sheet here. And hopefully those are lined up. So you can see that at least the black lines on this are close enough to line up to the blue lines. And so now we take our purple sheet. We get the beginnings lined up. There we go. One more way. And they start out pretty well lined up together. This would be an example of constructive interference if they're both peaking at the same time and playing at the same time. But as we go, it gets a little bit more and more off. And I'm hoping that you can see the black lines on the transparency and then the purple line underneath it. So it starts out with constructive interference, and actually within this range, it's still constructive, but it eventually gets to destructive. So if you add the two waves together, so if they played two notes at the same time, this is what it would look like. Those each had an amplitude of 1, and then together they start out at an amplitude of 2, and that amplitude is getting smaller as we go. If we then took it even farther, it would look like this. Complete destructive interference here, complete constructive interference here, or close enough. And so it's loudest, quiet, and then it gets loud again, and then quiet again. So what that sounds like is the following. Let's put this at 440. We play 440. I assume all of you have that sort of memorized now. And let me play 439. Could you notice the difference between those?
No.
Occasionally, I do have people whose ears are tuned well enough to be able to tell the difference. I cannot. But let me play them at the same time. So what you're getting is that the wah-wah sound is exactly what I was showing you on the graph there on the plot. You get the loudest, and then it goes quiet, and then it gets loud again. Now, how often it gets quiet is known as the beat frequency, or how frequently it becomes quiet is known as the beat frequency. And get ready for the math involved. So I play 440 hertz. That was frequency 1. Frequency 2, 439 hertz. And then the sophisticated math, the beat frequency is I subtract, and I get 1. This is the beat frequency. So if the beat frequency is 1 hertz, what's the beat period?
It'd just be 1 over 1, right?
Yep. So 1 units?
Seconds?
Yeah. So it should go quiet every second. Once a second. So let's crank this up again. 1001, 1001, 1001, 1001. If I now, let's stop that one and stop that one, which I actually turned them off. Okay. I'm now going to do 440 and 439.5. So first, let's predict. So if I'm playing 440 hertz and 439.5 hertz, what's the beat frequency?
0.5.
Just subtract 0.5. And therefore, so that is the beat frequency. And then the beat period?
2 seconds.
2 seconds. Just the reciprocal of 0.5. Let's see if it actually works. That's 439.5 and 440. 1001, 1002, 1001, 1002, 1001, 1002. So we can tell if I'm playing 2 notes how close they are together by the beats. If I'm not hearing any beat frequency, that means that either I've hit it exactly or I'm so far away that the ear can't really distinguish. And I'm hoping we'll be able to hear something when we play that. So our prediction for the second harmonic was 408.3. And now we'll play this on top of it and see if you can hear at least a trill. I have a hard time hearing this. So we get this going first. Can you hear a little bit of a trill there without it? Come on. Occasionally I can get it long enough to hear that sort of sound. So at least we're close enough that there's some beat going on there. But perhaps I can maintain the third harmonic a little bit better. So let's go for our prediction for the third harmonic. Third harmonic down here. wavelength is 2/3 of L.
.56 meters.
Say again?
5.6
5.6.
meters.
All right. So our third harmonic, it was 0.56 meters. Our frequency would be 343 divided by 0.56. 612. 612 point
5 hertz.
hertz. That's not like the zero over there. It's like 612. A little bit of a trill there. Not as close as I think with the other two demonstrations of this, but at least hopefully close enough that there's some legitimacy to what I'm telling you. And it should just get worse from there, so we actually won't take it all the way through. Now, yeah, I don't have any other people with gray hair in here. Okay, so I'm curious though about, as you get older, you start losing the ability to hear certain frequencies. And there you go. Good. Not the one I wanted. Sweep generator, there we go. So, oops, did I turn that on? Okay, so it's basically going to start at 1 hertz and start working its way up. So what I would like you to do is when you first hear a sound, just sort of raise your hand, then you can put it back down, but just raise your hand when you hear the first sound. And then at the end, when you stop hearing it, just raise your hand. I'm going to crank this up. Personally, I'm going to lose hearing somewhere from around 8,000 to 10,000 hertz, and then I'll get it back again shortly before I lose it again. So let's put this up to 20,000. Oh, probably longer than 10 seconds. So over the course of a minute. I guess we heard that one immediately. $6,000 hertz. 7,500, I'm out. I hear it again. And it's gone again. We're at 14,000 hertz. 16,500. So we just went out at 18,000. And then that's 20,000 there. The older you get, it starts to, I had a physics explanation for it, and then I got corrected by some student who had apparently biology sometime in the past 30 years, unlike me. That I guess the bones in the ear, that the those sort of get worn down over time, and so you start to lose some of the higher frequencies. We're gonna go with that unless someone corrects me. That's right? Okay. Now, I was setting this up for a class years ago, and just making sure that I had access to it. And I was playing it at, I think it was somewhere around 15,000 hertz. And I couldn't hear it. I thought, it was off. I thought I hit stop, and so I started conducting class, and someone says, does anyone else hear that high-pitched noise? I left it on accidentally. And then once in a moment of pettiness, some students were outside my office being way too noisy, so I put it up, but I couldn't hear it. And got them to go, does anybody hear that? So, the one advantage of hearing loss right there.
Now my ears are ringing.
There's a certain amount of after effect, I believe.
Was it just near, like, as it went higher, did it start, like, waving? Cause it's like,
I was
louder
doing
than
it because when I first put it in my hand, because that was when it dropped, but then it came back on a little bit later.
And I wonder how much of that is the speaker itself as opposed to hearing.
okay, cause I could hear it, it was just like,
Yeah.
like louder than softer, kinda like when you're doing two frequencies at once,
Okay.
where it was like waving higher, so I didn't say I couldn't hear it, cause I could, it was just like getting louder and softer a little bit.
I kind of wonder if my brain was trying to ignore it to some extent.
Oh, I mean, that's one of the, for tinnitus, that's one of the techniques used to get rid of it. Or at least one form of it is, you start playing, you train the brain to ignore that frequency so that you don't hear the ringing in your ears. So, brains are weird, I think that's what it comes down to. All right, want to stretch our legs, come back, we will talk about some of the missing topics. We'll get into Doppler effect and show the video that got this banned in 4 countries. Yeah, I'm still wondering why that was banned as opposed to some of the other stuff, but maybe it's the bridge collapse that it didn't like.